3-phase bridge inverter for 120 mode of operation. మనకి దీంట్లో 2 టైప్స్ ఉన్నాయి 3-phase bridge ఇన్వర్టర్లో. ఒకటి వచ్చి 120 డిగ్రీ మోడ్ ఆఫ్ ఆపరేషన్, ఇంకొకటి వచ్చి 180 డిగ్రీ మోడ్ ఆఫ్ ఆపరేషన్ అన్నమాట. ఓకేనా. సో ఇప్పుడు ఫస్ట్ మనం 120 డిగ్రీ మోడ్ ఆఫ్ ఆపరేషన్ గురించి చూద్దాము. ఇది బేసిక్ డయాగ్రామ్ ఆఫ్ 3-phase bridge ఇన్వర్టర్ ఫర్ 120 డిగ్రీ మోడ్ ఆఫ్ ఆపరేషన్. సో ఇందులో మనం చూసినట్లయితే మనకి ఈజీగా అర్థమవుతుంది ఏంటంటే, ఇదేమో స్టార్ ఇంపెడెన్స్ లోడ్ అనేటువంటిది ఈ 3 ఫేసెస్కి కనెక్ట్ అయి ఉందన్నమాట. ఓకేనా. అంటే 3 ఫేసెస్ కనెక్ట్ అయింది అంటే ఈ ఫేస్ ఏ, ఫేస్ బి, ఫేస్ సి, ఈ 3 ఫేసెస్కి ఈ స్టార్ కనెక్టెడ్ ఇంపెడెన్స్ అనేటువంటిది కనెక్ట్ అయిందనమాట. ఇది న్యూట్రల్ పాయింట్. బేసికల్గా ఇక్కడ మనం డిస్కస్ చేసుకునేది ఈ డయాగ్రామ్లో ఏవైతే మనకు బేసిక్ పాయింట్స్ ఉన్నాయో ఆ బేసిక్ పాయింట్స్ గురించి మనం డిస్కస్ చేసుకుంటాము. పెద్దగా టెన్షన్ పడాల్సిన అవసరం లేదు. బేసిక్ పాయింట్స్ ఏవైతే ఉన్నాయో ఆ బేసిక్ పాయింట్స్ మనం అబ్జర్వ్ చేసినట్లయితే ఈ డయాగ్రామ్లో ఏవైతే మనకు కనిపిస్తున్నాయో వాటినే మనం బేసిక్ పాయింట్స్ కింద రాసుకుంటాము. ఓకేనా. సో పెద్దగా దాన్ని మనం స్టడీ చేసి చదివి రాయాల్సినంత అవసరం లేదు. సో ఇక్కడ మనం ఫస్ట్ చెప్పుకోవాల్సిన పాయింట్ ఏంటంటే, ఇది ఇన్వర్టర్ కాబట్టి ఇక్కడ మనం DC ఇన్పుట్ వోల్టేజ్ తీసుకుంటున్నాము. సో హియర్ ఇన్పుట్ వోల్టేజ్ ఈజ్ ఏ VDC input voltage. And the second point here, top of all 3 thyristors of 3 phase having a odd thyristors, those are T1, T3 and T5, and bottom thyristors we are taking even thyristors. So those thyristors we are taking T2, T6 and T4. Okay, so these 3 phases A, B, C phases connected for 3 star connected impedances load. Okay, and here the major important point is each and every odd thyristor perform the conduction with even thyristors but not a same phase even thyristor. అంటే ఇక్కడ ఉన్నటువంటి ఆడ్ థైరిస్టర్స్ అనేవి ఈవెన్ థైరిస్టర్స్ తోటి కండక్షన్ని పెర్ఫామ్ చేస్తాయి. అంటే ఎట్ ఏ టైము 1 పెయిర్ ఆఫ్ థైరిస్టర్ అనేది కండక్షన్లో ఉంటుంది అనమాట. ఆ 1 పెయిర్ ఆఫ్ థైరిస్టర్ కండక్షన్ ఏంటి అంటే, ఒకటేమో ఆడ్ థైరిస్టర్, ఇంకొకటేమో ఈవెన్ థైరిస్టర్ అయి ఉంటుంది అనమాట. అయితే ఈ ఆడ్ థైరిస్టర్ ఈవెన్ థైరిస్టర్ తోటే కండక్షన్ పెర్ఫామ్ చేసేటప్పుడు ఈ ఆడ్ థైరిస్టర్ యొక్క సేమ్ ఫేస్ ఈవెన్ థైరిస్టర్ ఏదైతే ఉంటుందో దాంతోటే కండక్షన్ని పెర్ఫామ్ చేయదు అనమాట. అంటే T1 అండ్ T4 కండక్షన్ అనేది పాసిబుల్ అవ్వదు. ఓన్లీ పాసిబిలిటీ ఏముంది, T1 హ్యావింగ్ ఏ 2 పాసిబిలిటీస్, వన్ ఈజ్ ఏ T2, అనదర్ వన్ ఈజ్ ఏ T6. Okay, so it's mean T1 odd thyristor perform the conduction with even T6 and T2 thyristors. If T3 thyristor having a 2 possibility of conduction, so T3 and T2 and T4, T6 is not possible because this T6 even thyristor connected for same phase. Okay, and T5 odd thyristor perform the operation with T6 and T4, but in the sequence order we are going to take AB and BC and CA. So this is the sequence order to perform the conduction status. So in that also we are going to take for each and every period of conduction we are going to take 0 to 60 degrees. It's mean 1 pair of thyristor conduction is 60 degrees only. Okay, if we are going to conduct T1 and T6, these one having 60 degrees and T1 and T2 having 60 degrees, totally 120 degrees of one phase having a 120 degrees. It's mean phase A odd thyristor T1 perform with T6 and T2, so it's mean A to B and A to C. Okay, so this is the actual phenomenon of conduction period, and here we are going to take that conduction period 0 to 60 degrees, 60 to 120 degrees. So that one is omega t equal to 0 to 60 degrees, 60 degrees to 120 degrees. That one is T1 and T6 and T2 thyristor will be going to in conduction period. It's mean T1 will be going to conduct with T1 and T6 and T1 and T2, and omega t equal to 120 degrees to 240. Okay, so this duration of time period T3, T2, T4 will be going to conduct. It's mean T3 and T2 and T3 and T4. Then again omega t equal to 240 to 360 degrees. So this duration of period T5, T6, T4 in conduction. It means simply T5 and T6 and T5, T4 will be going to conduct anamata. Okay na? So the same points I have written here. You have to observe. The above figure shows total 6 thyristors are there. So one from odd number of thyristor and another from even number of thyristor. Top side and odd thyristors and bottom side even thyristors. The above figure shows totally 3 phases, phase A, B, C respectively, and star connected impedance load. Same points. So the operation also here whatever I have discussed previously the same operation. For the 120 degree mode VSI, each thyristor conduct for 120 degree of cycle. Okay, so here voltage source inverter, VSI means voltage source inverter. So 120 degree mode of inverter requires 6 steps, each of 60 degrees duration for completing one cycle of the output AC voltage. Each and every pair of thyristor conduct conduction angle is 60 degrees. Okay, each and every odd thyristor perform conduction with 2 even thyristor, but none other than same phase even thyristor. నేను చెప్పింది అదే. సో ఏదైతే సేమ్ ఫేస్ ఉంటుందో సేమ్ ఫేస్లో ఉన్నటువంటి ఈవెన్ థైరిస్టర్ తోటి అది కండక్షన్ పెర్ఫామ్ చేయదు, అదర్ థైరిస్టర్స్తోనే అదర్ ఈవెన్ థైరిస్టర్స్తోనే కండక్షన్ పెర్ఫామ్ చేస్తుంది. వన్ ఆడ్ థైరిస్టర్ హ్యావింగ్ ఎ 2 పాసిబిలిటీ ఆఫ్ కండక్షన్ విత్ ఈవెన్ థైరిస్టర్స్. That's why each and every phase perform conduction angle is 120 degree, 2 pairs of conduction. Okay, so here 2 pairs of conduction possible, 2 pairs of conduction 120 degrees. For example, T1 conducts with T6 and T2 at omega t equal to 0 to omega t equal to 60 degrees. T1 and T6 in conduction at omega t equal to 60 degrees to omega t 120 degrees, T1 and T2 in conduction. So it means simply we can divide totally one full cycle 360 degrees. That's 360 degrees we are dividing each and every one pair of thyristors in conduction. So for each and every pair of conduction 60 degrees only. So that's why totally 60 into 60 360 degrees. Similarly T3 conducts with T2 and T4. So at omega t equal to 120 degrees to omega t equal to 240 duration, this period T3 and T2 in conduction. T3 and T4 thyristors are in conduction mode respectively. So T5 conducts with T4 T6 during the omega t equal to 240 degrees to omega t equal to 360 degrees. If T5 T4 in conduction during omega t equal to 240 degrees to 300. At the same time T5 and T6 in conduction during at 300 degrees to omega t equal to 360 degrees. Okay, so first we are going to calculate phase voltages. So from omega t equal to 0 to omega t equal to 60 degrees, T1 and T6 in turn on condition in between phase A and phase B. So once we can observe here the diagram clearly, the conduction mode we are going to take here. So T1 and even thyristor T6 and T2 is possible for T1. because the same event thyristor is not possibility to conduct. So that's why T1, T6 and T1, T2. So whenever we are going to take in a sequence order only, so it's mean A phase odd thyristor perform with A, B and A, C. A having odd thyristor T1 and B phase having even thyristor T6, and say at the same time A phase T1 odd thyristor and with C phase even thyristor T2, like that only. Okay, and at the same time here we are going to take odd thyristor T3 in the sense, so this one is B, no, so it will be a sequence of T3 and T2. It's mean phase B and phase C. Phase B odd thyristor and phase C even thyristor. Okay, so that's why T3 and T2. So this one is completed, and one more possibility also there. That possibility is T3 and T4. So BC and BA, sequence order only. Then T5 in the sense we are going to take this T5 with CA in the sense T5, T4, that one is a sequence order, and T5 and T6 is another sequence order. The same sequence order you can follow in the sense, then only you will be going to get one perfect triggering pulse, and as well as waveforms also we are getting in the same manner. So first we are going to calculate phase voltage from omega t equal to 0 to omega t equal to 60 degrees. That one is a T1 and T6 in turn on condition in between phase A and phase B. Okay, so this is the first order. So here we have a VDC equal to T1 and T6. T1 and T6 only the first conduction period here. Okay, you don't forget it. Okay, if there is a one more possibility, that one is T1 and T2, but you don't write first T1 and T2, you have to write T1 and T6 in a sequence order only. Okay, so here T1 is a forward mode of thyristor, and T6 is a reverse direction of the T1. Okay, it's mean T1 and T6, these two are in anti-parallel only. So here also you can observe here T1 in downward direction, so it's mean this one is T1 phase A to Z, and as well as neutral point to Z again, and it return back to B phase, and B phase to T6 to return back to the VDC. The same diagram I have drawn here. VDC to T1, T1 to A phase to Z, and Z to neutral point, and neutral point to Z, and Z to B, and B to T6, and T6 to return back VDC. The same whatever the diagram, basic diagram we have taken, the same sequence order. VDC, T1 and phase A to Z, Z to neutral to Z, and again return back to B, and this one is reverse bias. Now there is no any flow of current through this thyristor, that's why here T6 to return back to VDC. The same diagram I have drawn here. Okay, and here we can apply voltage divider rule. So the voltage divider rule is V into opposite resistance by total resistance. Here resistance plus we can replace impedance only, that's why here opposite resistance in the sense VDC opposite we have a Z. Okay, so divided by total resistance in the sense this Z and this Z, and it's mean total resistance in the sense total impedance. So that's why here we are going to take VAN. So we are going to take for these three values, then VDC here, VAN in the sense VDC, and as well as opposite resistance Z by Z plus Z. So from the voltage divider rule, V naught equal to V into V in the sense here input voltage, that one is VDC voltage, so V plus we can replace VDC, and opposite resistance place we can take opposite impedance Z by total resistance, in the sense total impedance Z plus Z. Here two Z's are there. So then what will happen here? VDC Z equal to 2 Z plus Z, in the sense 2Z. So that's why here Z and above numerator Z is there, no? So that Z and bottom Z, those two are cancel in the sense, then we can get VDC by 2. And same like VBN. VBN. I mean VBN in the sense this one and this one and this one. Okay. But here this one is a forward, and for this one is a reverse. So that's why we are taking minus here. So minus VDC into Z opposite resistance by total resistance Z plus Z. Okay, that is equal to, here same Z plus Z is 2Z, Z and Z cancel, then we can get minus VDC by 2. And here there is no any C and neutral, and C phase is not there, only A and B phases only there here. That's why VCN equal to simply 0. From omega t equal to 60 degrees to 120 degrees, T1 and T2 in turn-on condition in between phase A and phase C. Same like previously I have said, now T1 and T2 in turn-on condition. That one is phase A and phase C. Okay, these two are in conduction mode. Okay, previously these two in conduction mode, A, B phase madhyalo T1 and T6 in conduction mode. Then right now T1 and T2 in conduction mode. So the same operation and the same calculation. Okay, so the first one we are going to take here VDC A and as well as Z, and neutral and as well as Z, again C, and as well as T2 return back to the VDC. So here first we are going to calculate VAN phase voltage. VAN phase voltage in the sense VDC and as well as opposite resistance, in the sense opposite impedance by total impedance. So that one is VDC by 2. So here VBN is not there. Okay, here only A phase and C phase only, B phase is not there. So that's why simply we are going to take VBN equal to 0. And here VCN equal to, so this VCN is reverse direction of this VAN. So that's why here we are going to take minus VDC Z by Z plus Z equal to minus VDC by 2. Same calculations. And for next, from omega t equal to 120 degrees to omega t equal to 180 degrees, T3 and T2 in turn-on condition in between phase B and phase C. Okay, so right now phase A is completed. So it's mean our thyristor T1 is completed. Then we are going for T3. Okay, T3 also having a two possibilities. One is B, C phase having T3 and T2 first conduction, and next T3 and T4 second conduction. Okay, so here totally 6 conduction modes only. So T1 having a 2 possibilities, T3 having a 2 possibilities, and T5 having a 2 possibilities. Totally 6 pair of conduction, 6 into 60, 360 degrees pair of conduction. Okay, then we are going for here 120 degrees to 180 degrees, T3 and T2 in turn-on condition. Then here this one is a VDC, and that VDC VBN, first we are going to take VBN. Here neutral is there, neutral point. Then VBN equal to VDC Z by Z plus Z equal to VDC by 2. Same operation and same derivation. Then we are going for VCN neutral point here. Okay, so it's mean this one is forward direction and this one is reverse direction. That's why we are taking minus VDC Z by Z plus Z equal to minus VDC by 2. Here VAN phase is not there, only B phase and C phase only there. So A phase is not there. That's why here we are taking 0 value. Okay, then we will go for next. Omega t equal to 180 degrees to omega t equal to 240 degrees, T3 and T4 in turn on condition in between phase B and phase A. So here first one is VBN. So VBN having VDC Z by Z plus Z equal to VDC by 2, and VAN in the sense this one is a reverse direction, so compared to this direction, so that's why we are taking minus VDC Z by Z plus Z, that is equal to minus VDC by 2. Here C phase is not there, only B and A phase only there, so that's why here VCN equal to 0. From omega t equal to 240 degrees to 300 degrees. So T5 and T4 in turn on condition. Right now T3 is completed. So T1, T6, T1, T2 completed. Then T3, T2, T3, T4 completed. Then we are going for T5 to T4 first sequence. So CA. Then next T5 to T6. That one is the next sequence. Okay. So here T5, T4 in turn on condition. Then here VCN. We are taking VCN in the sense that one is VDC Z by Z plus Z equal to VDC by 2. Then we are going to take a reverse direction here, VAN. This one is a reverse direction of flow of current. So that's why here minus VDC to Z by Z plus Z equal to minus VDC by 2. So for this one is a forward and this one is a reverse. So that's why here we are taking minus VDC by Z, Z plus Z equal to minus VDC by 2. So here only C phase and A phase only there, B phase is not there, that's why VBN equal to 0. Then last one, final one, from omega t equal to 300 to 360 degrees, T5 and T6 in turn on condition in between phase C to phase B. Okay, so first we are going to take a forward VCN. So VCN equal to forward now, so that's why according to voltage divider rule, VDC into opposite impedance by total impedance Z plus Z, that is equal to VDC by 2. Then again we are taking in a reverse direction VBN in the sense that one is minus VDC into Z by Z plus Z, that is equal to minus VDC by 2. And here only C and B phases are there, A and A phase is not there, that's why VAN equal to 0. Okay, and those are phase voltages. Then similarly we are going to calculate line voltages also. So line voltages in the sense phase A and phase B, between phase A and phase B we are going to take that one as a one line, and phase B and phase C, in between phase B and phase C we are taking that one as a one line, and phase C and phase A, it's mean in between phase A and phase C, that one is one line voltage. So we are going to calculate line voltages here similarly like phase voltages. First we are taking from 0 to 60 degrees T1 and T6 in turn on condition. So in that particular condition VAB equal to VAN minus VBN, that is equal to, so already we have calculated VAN and VBN value at 0 to 60 degrees angle. So those values only we are going to take here, 0 to 60 degrees T1 and T6 in conduction mode. So here this one is a phase voltages. From these phase voltages we are going to calculate line voltages here. It's mean in between A phase and B phase one line voltage. So that line voltage value we are going to take VAN minus VBN. VAN value is VDC by 2. Okay, and as well as VBN voltage here minus VDC by 2. Same, once we can calculate phase voltages, then it will be a very easy for to calculate line voltages. So these two values we are going to substitute here, VAN plus VDC by 2 and VBN plus, here already minus is there, and VBN also having minus VDC by 2. So minus of minus VDC by 2. So this one we are going to calculate add these two values. So VDC by 2 plus VDC by 2, that is equal to VDC. Okay, then VBC in the sense in between phase B and phase C voltage is line voltage. So VBN, here whatever the variables we are taking A and B, no, so those values only we can divide, VAN and VBN. So here N is a neutral point and A is a phase voltage. So phase A voltage, phase A and neutral voltage minus phase B neutral voltage is called a VAB line voltage. Same like VBC in the sense VBN neutral voltage. So it's mean B phase and neutral B phase ki neutral point ki రెండిటి మధ్యలో ఉన్నటువంటి voltage minus VCN C phase ki neutral wire ki మధ్యలో ఉన్నటువంటి voltage, ఈ రెండిటిని సబ్ట్రాక్ట్ చేస్తే then we are getting VBC line voltage. So here VBN already we have calculated, that one is minus VDC by 2, that value we have substituted here, and VCN here 0, that's why VCN 0, that is equal to minus VDC by 2 only. Then we will go for VCA in the sense C phase and neutral voltage minus A phase neutral voltage, that is equal to VCN in the sense here VCN is 0 at 0 to 60 degrees condition, VCN is 0 minus VDC by 2, VAN is minus VDC by 2, so that's why minus VDC by 2, that is equal to minus VDC by 2. Similarly we are going to calculate for 60 degrees to 120 degrees. So 60 degrees to 120 degrees we have these two values, VAN is VDC by 2, so that's why here VAN plus we can replace VDC by 2 minus VBN is here 0, 60 degrees to 120 degrees, VBN is 0, so that's why VBN is 0 here. Then we can get VDC by 2 and VBC equal to VBN minus VCN, that is equal to VBN here 0 and VCN is minus VDC by 2, that's why minus of minus VDC by 2, that is equal to VDC by 2, and VCA equal to VCN minus VAN, that is equal to minus VDC by 2, minus VDC by 2, that is equal to minus VDC. Similarly we are going to calculate for 120 degrees to 180 degrees T3 and T2 in turn on condition. Similarly the same line voltages, and similarly 180 degrees to 240 degrees T3 and T4 in turn on condition, line voltages. Similarly you have to calculate same like previously whatever we have discussed, the same manner. And from 240 degrees to 300 degrees T5 and T4 in turn on condition, line voltages values, and here 300 to 360 degrees T5 and T6 in turn on condition, line voltages. Okay, so we have calculated phase voltages and line voltages. Those phase voltages and line voltages we can replace in waveform. Okay, first we are going to take a VDC, that one is a DC voltage we are going to take here. So that value we can divide each and every pair of thyristor having 60 degrees conduction, so that's why we can divide with 60 degrees, 60 to 120, 120 to 180, 180 to 240, 240 to 300, 300 to 360. So this one is one full cycle. Okay, so first we have first phase, this one is phase A and this one is phase B and this one is phase C, we can take it. So this entire column is phase A and this entire column is phase B, this entire column is phase C. So phase A having here, phase A having T1 and T4 thyristors only. Is it right or not? The same T1 and T4 thyristors we are going to draw here. So it's mean T1 and T4, these two are each and every thyristor having 120 degrees. So T1, this one is 160 degrees, and T1, this one is 60 degrees, 120 degrees. After 120 degrees, we are taking delay angle. So after that 60 degrees delay angle, we are going to take T4 and T4. Okay, and here this one is again delay angle. So each and every thyristor having 120 degrees, and after that 120 degrees one delay angle. Okay, that like that only we are going to take here. And for phase B, compared to phase A and phase B, there is a 120 degrees phase shift. Is it right or not? So phase A started from 0 to 120 degrees T1 and 60 degrees delay angle. Then after 180 degrees to 300 120 degrees T4 thyristor and again delay angle. But here phase B start with after 120 degrees only. Phase shift is 120 degrees, no? So compared to phase A and phase B is 120 degrees. So 120 degrees started here, no? So that's why T3 started, phase B T3 started after 120 degrees. 120 degrees తర్వాత నుంచి స్టార్ట్ అవుతుంది అనమాట. ఓకేనా? T3 120 degrees to 240 degrees. And then 60 degrees delay angle. Then thereafter 60 degrees T6. So here even thyristor is T6, no? So in phase B. So in phase B even thyristor T6. So this one is only 60 degrees, and remaining 60 degrees it will be going to return back to the first place. Okay, and as well as delay angle. And compared to phase B and phase C, there is a 240 degrees phase shift. Okay, is it right or not? So we have a three phase having 120 degrees phase shift between two phases, phase A to phase B and phase B to phase C. So here phase C having a 240 degrees. So 240 degrees having a T5. Phase shift is here 120 degrees. So here to here is 120 degrees, but from here to here we are taking 240 degrees. So that's why C phase having a 240 degrees. So after 240 degrees only we are going to take T5. So here 240 this one, no? So after 240 only we are taking T5. Okay, that T5 is also a 120 degrees. 240 to 300, 300 to 360. Then again after 120 degree of this T5 we are taking delay angle 60 degrees. Return back to starting. That after delay angle, then we are going to take T2 120 degrees. Here even thyristor is T2, no? So that even thyristor T2 we are taking 120 degrees. After 120 degrees again 60 degrees delay angle. Okay, so each and every phase having 120 degrees phase shift. That's why first A phase started from 0 after 120 degrees delay angle and 120 degrees again delay angle. B phase start with 120 degrees because 120 degrees phase shift, and T3 started after 120 degrees, and delay angle T6, and again T6 is in starting 120 degrees, and phase C is started with 240 degrees. Okay, phase shift from 240 to T5 and T5, and here delay angle and T2 and delay angle. Okay, this is the actually we are going to take. And one more thing is, you remember whenever we are taking these thyristors, so we are taking this one is a column, no? If we are going to take a line, in the sense that line will be going to match here. First pair of conduction start T1 and T6, no? Is it right or not? T1 and T6. So that one will be going to match here. Otherwise this one is wrong. Whatever the waveform we have drawn, no? So that one is wrong. Okay, and next pair of conduction is T1 and T2. Is it right or not? T1 and T6. So from A to B phase and A to C phase, T1 and T2. That T1 and T2 is need to match. Okay, and again we are going to take a T3, no, R thyristor T3, and this T3 is conduct with T2, so it's mean T3 and T2 next one, T3 and T2 next 60 degrees, and again T3 and T4. Okay, is it right or not? So the same phase even thyristor we are not taking. T3 and T2 is one conduction and T3 and T4 is another conduction here, T3 and T4. Okay, and T5 we are going to take in the sense that T5 and T4 first conduction, T5 and T4 first conduction, and again T5 and T6 next conduction, T5 and T6. సో ఈ విధంగా మ్యాచ్ అయితేనే ఈ సీక్వెన్స్ ఆర్డర్లో అప్పుడు ఈ వేవ్ ఫామ్ కరెక్ట్ అన్నట్టు. దెన్ వీఆర్ గోయింగ్ టు డ్రా ఫస్ట్ ఫేస్ వోల్టేజ్, ఓకే, VAN. So whatever the VAN we have calculated from 0 to 360 degrees, the same values we are going to put here. So already we know that 0 to 60 we have taken phase voltage VAN VDC by 2. Already we know that VAN is VDC by 2. That VDC by 2 we have run here, and 60 to 120 degrees same phase voltage, 60 to 120 degrees same VAN VDC by 2 only. So VDC by 2 extend చేసాం సిమిలర్గా, ఓకేనా. దెన్ నెక్స్ట్ 120 degrees to 180, 120 degrees to 180 తీసుకున్నట్లయితే VAN ఏముంది, 0 ఉంది. సో కాబట్టి 0 తీసుకొచ్చాం, ఓకేనా. 180 degrees to 240, 180 degrees to 240 ఏముంది, VAN మైనస్ VDC by 2 ఉంది. సో కాబట్టి మైనస్ VDC by 2 కింద రాసాం. నెక్స్ట్ 240 to 300 ఏముంది, VAN మైనస్ VDCనే ఉంది సేమ్, కాబట్టి ఎక్స్టెండ్ చేసాం. నెక్స్ట్ 0 సిమిలర్గా వచ్చిందనమాట. సేమ్ అదేవిధంగా VBN కూడా డ్రా చేయాలి. VBN 0 to 60 degrees ఎంత ఉంది, మైనస్ VDC by 2 ఉంది. నెక్స్ట్ 60 degrees to 120 degrees VDC ఈక్వల్ టు 0 ఉంది. నెక్స్ట్ 120 degrees to 180 అండ్ 180 degrees to 240 రెండు కూడా VDC by 2 VDC by 2నే ఉంది. 240 to 300 వచ్చి VDC ఈక్వల్ టు 0 ఉంది, అండ్ 300 to 360 వచ్చి మైనస్ VDC by 2 ఉంది. సిమిలర్గా VCN ఫేజ్ కూడా డ్రా చేస్తాం. VCN ఈక్వల్ టు VDC ఈక్వల్ టు 0, అది దేనికి 0 to 60 degreesకి. సేమ్ 60 to 120, 120 to 180కి వచ్చి మైనస్ VDC by 2 మైనస్ VDC by 2 ఉంది, ఓకేనా. నెక్స్ట్ మళ్ళీ 0 ఉంది VDC. నెక్స్ట్ 240 to 360 వరకు VDC by 2 VDC by 2నే ఉంది. ఇవి ఫేస్ వోల్టేజెస్. దెన్ వీఆర్ గోయింగ్ టు డ్రా లైన్ వోల్టేజెస్. లైన్ వోల్టేజెస్ ఇన్ ద సెన్స్ ఆల్రెడీ వీ హ్యావ్ క్యాలిక్యులేటెడ్ లైన్ వోల్టేజెస్. సో VAB, okay, so we are going to see line voltages. Here you remember VAB equal to VDC. VDCనే కదా వచ్చింది. సో లైన్ వోల్టేజ్ VDC. ఎందుకు ఇట్లా స్టెప్ కింది VDC అనేది పెద్ద వాల్యూ కంపేర్ టు VDC by 2 కాబట్టి. సో నెక్స్ట్ సేమ్ 60 degrees to 120 degreesకి ఏమొచ్చింది, 60 to 120 degreesకి VAB 60 to 120 degreesకి VAB ఏమొచ్చింది, VDC by 2 వచ్చింది. కాబట్టి ఆ VDC by 2ని ఇక్కడ రాసాం ఒకటి తగ్గించి, ఓకేనా. నెక్స్ట్ 120 to 180కి ఏమొచ్చింది, 120 to 180కి ఏమొచ్చింది, మైనస్ VDC by 2 వచ్చింది. కాబట్టి దాన్ని కిందికి రాసాం మైనస్ VDC by 2. నెక్స్ట్ 180 to 240కి ఎంత వచ్చింది, VAB మైనస్ VDC వచ్చింది. మైనస్ VDC అనేది మైనస్ VDC by 2తో కంపారిజన్ చేస్తే ఎక్కువ కాబట్టి అది రాసాము. మళ్ళీ స్టెప్ కిందికి వచ్చి సిమిలర్గా వస్తాయన్నమాట, ఓకేనా. సేమ్ సిమిలర్గా VBCకి డ్రా చేస్తాం, VCAకి కూడా డ్రా చేస్తాం. సింపుల్ వేవ్ ఫామ్, ఓకేనా.